Welcome to The Explainer. I am absolutely thrilled to have you here today. If you're gearing up for your Cambridge AS and A-level computer science exams, specifically Syllabus 9618, you are in exactly the right place. Today, we're dissecting the exact strategies you need to master writing pseudocode for 2D arrays. It's a bit like being a high-end fashion designer. You have to tailor your answer to fit the question perfectly. No loose threads. We aren't just memorizing syntax here. We're unlocking the underlying algorithmic logic examiners are literally hunting for. So get comfortable, focus in, and let's decode this whole shebang together.
Okay, let's dive into this. We have a direct quote from a senior Cambridge examiner, and it completely sets the stakes for everything we're about to cover. They said, "The difference between a B and an A in computer science often comes down to how well you understand writing pseudocode for 2D arrays." Seriously, this topic is the great separator. It's the exact hurdle that trips up good students, but propels great students right into that top grade boundary.
To get you straight to that A-star level, here's our roadmap. We'll cover the A-star difference, the method mark strategy, the top 3 examiner warnings, our technical execution steps, and finally, how to master critical analysis. Let's get moving. Starting with Section 1, the A-star difference. We are moving from superficial breadth to analytical depth. It's absolutely vital to understand that Cambridge assessment objectives target very specific cognitive domains: knowledge, application, and pure analysis. Which brings us to a really fascinating question. Why do students find interpreting complex binary representations, especially within arrays, so incredibly hard? Well, top-performing students overcome this by building connected, conceptual understanding. They don't just see a 2D array as a random grid of data. They see the relationship between the indices, the memory structure, and the data itself. And that's what allows them to transfer their knowledge to completely unfamiliar, high-pressure exam contexts. Imagine 2 students taking the exact same exam. Let's call them Alex and Sam. Alex overloads the answer with raw computer science facts, just throwing generic knowledge at the page, hoping something sticks. That's superficial breadth. Sam, on the other hand, delivers analytical depth. Sam uses logical, structured, and evidence-based reasoning. This perfectly illustrates what examiners are looking for. When you write pseudocode, every single line must have a deliberate analytical purpose. You can't just be Alex, you've got to be Sam. Moving into Section 2, the method mark strategy. This is all about surviving flawed execution. Look, exam conditions are stressful. Sometimes your logic just breaks down halfway through an algorithm, right? But there's a safety net built into the marking scheme. The crucial point here is the method mark strategy. This is an assessment protocol where marks are explicitly awarded for demonstrating the correct procedural process and clear working, regardless of your final code execution. Basically, you must show your working systematically. If you just write down a final broken loop, you get 0. But if you show the logical steps leading up to it, you salvage crucial marks.
This alert straight from the examiner says it all. Even if your final answer is wrong, method marks can save you. Procedural discipline actively lowers your exam anxiety because you know that every correct step you take is banking points. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button right now.
All right, Section 3, the top 3 examiner warnings. We're going to do a quick autopsy of failed algorithms. We're shifting our tone a bit here because, based on principal examiner reports, thousands of students lose their marks in the exact same ways. There are exactly 3 massive pitfalls you must absolutely avoid when writing pseudocode for 2D arrays. Eliminate these 3 errors and your grade will automatically jump.
So, what are they? First, vague and non-technical answers. Examiners are not looking for casual descriptions. They want precise, technical terminology. Second, forgetting boundary conditions and edge cases. Think about it. What happens at row 0? What happens at the maximum array index? Students constantly forget to check these limits. And third, ignoring the specific context of the question. You literally cannot write a generic search algorithm when the command words in the question explicitly ask you to filter a specific dataset. Think about the contrast between these 2 approaches. On one hand, you have a generic, vague answer that completely ignores the scenario. That's going to lose points every time. On the other hand, a context-specific, technical answer directly addresses the problem's data constraints. Remember our fashion designer metaphor? This is where you tailor your answer to fit perfectly. It's the ultimate difference between a candidate who just memorized a textbook and one who is actively solving the problem in front of them. To help lock this in, you should create your own memory hack.
Maybe try an acronym for technical detail, boundaries, context, TBC. Whatever works for your brain, invent a hack to recall these vital factors before you write a single line of pseudocode. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at aceexams_IGCSE to excel in your Cambridge examinations. We've helped so many students improve, so join them right now. Section 4, Technical Execution Steps. Let's look at the algorithmic blueprint. We've gone over the warnings, so now let's focus on the actionable solution. This right here is your standardized execution sequence. Step 1. Deconstruct the question. What command words are actually being used? Step 2. Extract relevant data, whether that's from binary representations or a given dataset. Step 3. Select your analytical framework, like which loops or structures are needed. Step 4. Execute with clear notation. And Step 5. Present with correct terminology. Follow these 5 steps and you're actively performing the exact systematic processing the syllabus demands.
Let's move on and see how this builds into broader algorithmic thinking. Those execution steps slot directly into these 4 core skills: step-by-step decomposition, selecting the appropriate data structure, efficient code implementation, and finally, rigorous testing. This is the complete blueprint of a top-tier computer science student. Finally, Section 5, Mastering Critical Analysis, Thinking like an Evaluator. We have reached the final tier of mastery. This is the key to separating good programmers from truly great ones, evaluating the code itself. Top-scoring candidates constantly demonstrate this evaluative thinking. If there are multiple solutions, they consider the alternatives. They analyze the trade-offs between different approaches. They readily acknowledge the limitations of their own algorithms, and most importantly, they provide justifications supported by concrete evidence. They don't just say an algorithm is better, they prove exactly why. And how do they prove why? By using specific quality metrics. Evaluating performance requires identifying technical constraints, time complexity. How does the execution time scale as that 2D array gets larger? Space complexity. How does the memory usage scale? And of course, edge cases. How does the algorithm handle extreme boundary conditions? Dropping these terms into your answer proves your analytical depth. I really want you to think about this question for a second. How does failing to identify just one edge case affect your algorithm's overall performance? The scary reality is, it can cause the entire system to crash. It highlights the absolute fragility of algorithms that haven't been rigorously tested at their boundaries. This is exactly why examiners penalize you so heavily for missing them. So, let's bring it all together. Here is your final takeaway. Method marks save grades. Always, always show your procedural working and practice past paper questions relentlessly. Apply the blueprint, check for boundary conditions, and use your technical terminology. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Turn on all notifications so you never miss a strategy session. I want to leave you with a provocative thought to reflect on before your next study session. Be completely honest with yourself. Which of the 3 examiner warnings, vague answers, ignoring boundaries, or missing the context, is currently costing you the most marks in your practice papers? Identify your weakness right now. Drop a comment below with your biggest challenge, apply the strategies we discussed today, and go conquer that Cambridge computer science exam. Thanks for joining me on The Explainer, and keep learning.